This video will discuss simulating stock prices based on fitting a distribution to historical return data. So the data we have here are the multiplicative returns for the SPY index fund that we obtained from Python. And so now they're in an Excel file. So we're going to create a file to simulate the price 5 months from now. So we'll just create here a column for the next 5 months, and we'll have a beginning price for each month and a return for each month and an ending price for each month. Now the beginning price for the first month is going to be the last price in the list that we obtained from Python. So if I just want to scroll down, I'll find that that price is 560.62. But I can just copy this value here. And we'll just paste it here. Okay, so that'll be the beginning price. We'll jump off from where the previous prices ended. Now what we'll do is fit a distribution for the return. And so we're going to assume that these multiplicative returns have what's called a log normal distribution. And based on empirically the time series that these stock returns typically follow, that would be the distribution that they would have. So we'll see what that looks like. Well, what we want to do is fit the distribution to the data. So we're going to go up here to Fit. I'm on the At-Risk menu item here after opening At-Risk. And under Fit, we'll choose Fit. And it will bring up here this window. And so what we need to put in the range is the range of all of the multiplicative returns. So to highlight a range, we can click on this little red arrow and then just highlight this entire range of historical data and click OK. And this is continuous sample data, so we'll leave that button checked. Now, over on distributions, comes up with a whole list of the distributions. We're going to go down here to Select and go ahead and just hit Clear All. And then we're going to select the log normal distribution. Now, what we need to do is, for the log normal distribution, one thing we know is these multiplicative returns can't be negative. And so what we would do is click on a fixed bound here, and the fixed bound is 0. And so we want to fit the distribution with that bound. And then we'll click OK. And here is the at-risk fit for the log normal distribution. And so notice it compares this red line is what the distribution looks like, and the blue histogram is the original data. It looks a little bit like a log normal distribution, or excuse me, a normal distribution. A log normal distribution can, but there is a limit at 0 on the log normal distribution. So now what we're going to do is write this to Excel. Okay, and we can use the defaults here. And it'll come up and say choose a cell to place it, and we'll place it in the first cell, the month 1 return. And so now you can see up here the formula that's in this is an at-risk formula for this log normal distribution. Now that we have the multiplicative distribution, we can calculate the end price for month 1 as the beginning price times the return. Now to roll this forward to the second month, we would make the beginning price equal to the month 1 ending price. We can copy that down. We'll have separate returns for each month, but they'll have the same distribution, so we can drag this return formula down as well. And then, of course, the ending price formula. Now, what we're going to do is simulate this price after 5 months. So we'll click on the month 5 price and make that an at-risk output. And I'll just put ending price as the name and click OK. Alright, so now we can go ahead and simulate this price. I typically use 2,000 iterations. And so we can click Simulate and then start the simulation. Alright, and so At-Risk has run the simulation. And what At-Risk is doing in this simulation is actually simulating 2,000 different values for all of the returns. And so on each simulation trial, it simulates a different set of returns. And then we have a different set of end prices simulated. And so what this histogram here shows is the distribution of the 2,000 different ending prices that were simulated. Now these have a mean of 581.3, and you can see the other statistics. The beginning month 1 price was 560.62. If we wanted to know what percentage of the time the price after 5 months went down below 560.62, we could put that number in here and hit enter. And we can see that basically the stock price went down 38% of the time, or went up 62% of the time. Alright, now we're going to create another output, so we can close this. We're going to create an output called loss. And the loss would be a situation where the ending price was less than the beginning price. So if the beginning price minus the ending price is positive, we would have a loss. Now, right now this is a negative value because this 581 is greater than 560, but we know that there's 38% of the simulation trials where the stock price goes down. So we'll make this its own output called loss. And then we'll run the simulation again. You can get slightly different values than I'm getting here, of course, when you run a simulation, but they'll probably be fairly similar. Alright, so we see the average loss is negative, which means that on average, actually, the stock price goes up. But we know if we want to, for instance, put 0 here, we know that in this case, 39% of the trials, the stock price went down. Okay, because the loss is greater than 0. Remember, that was 38% in the last simulation, but since these are random numbers, we can get slightly different values. If we want to put in back, let's put 5% back in here. Okay, this 69.5 is called the 95th percentile of the loss distribution. If we scroll down on the right, we can also see the 69.5 as the 95th percentile. And so this has a special name, the 95th percentile of this loss distribution in finance. It's called the 5% value at risk. I'm just going to write that here, 5%, that the 5% value at risk is 69.5. So what it tells us is that 5% of the time, if we invest in this stock for 6 months, we're going to lose $69.5, which gives the investor some measure of risk that they can use to evaluate whether they'd want to make this investment. Now, one more number that we're interested in is what's called the 5% conditional CVAR. And the conditional VAR is the average of the 5% worst losses. So in at-risk, what we can do is create a filter, and that's right here where it says define filters. And we'll use filter type standard, and we'll filter using the percentiles. We'll start with the 95th percentile. And so notice what at-risk does. It basically just cuts off the tail of this distribution. And notice this number 70 is very close to the 69.5. Okay, so basically about 70 is the 5% VAR. But if we look at the average of the 5% worst losses, the average is 85.86. And again, it's just a measure of risk. On average, when we have 5%, the worst 5% of scenarios, we're losing 85.86. This might be a good window to save. If we wanted to save this window, we can go here to the blue arrow and export and do copy, grid, and graph, and then close. And if we put down here, we paste this. If we just want to save this, which is kind of nice to do, we can resize it if we want. But we've got now the graph saved. We've got 70, which approximately is the 5% VAR, and then the mean over here, 85.86, is the 5% conditional VAR.